we had the first webinar on last January, and this was organized within the topics of working group 1. As you know, the cost action is organized. This cost action is organized in 3 working group 1, 2, and 3. The seminar, the first one was focused on topics related to working group 1. Today we will have the second one focused on working group 2 topics. So we will go ahead with working group 3. I would like to thank you, Professor Hassan Emida, because I think that he was the main promoter of this initiative. And you know that this cost action must be kept alive during the years. And the way to keep the project alive is to contribute to a number of activities, not just the meeting that we will have periodically, but during all the time. With this type of activity is a way to keep the project running. So I'm very thankful for this initiative. I don't know, as before introducing the speaker, I don't know if Hassan, Professor Emida, wants to introduce or say something. Please, Hassan, if you want.
Well, I just want to say that this initiative actually is from everyone in this cost action. It has been actually announced in the last management meeting. And yes, it started this year and then fluctuates between the 3 different groups. We are happy to have Panos today. So Panos used to be in University of Birmingham working in civil engineering, and now he's in back to Greece in Chania. Panos, we are happy to have you today for this webinar, and I'm sure that this talk is not only for working group 2, it's for everyone in the 3 working groups 1 and 2 and 3. So that's everything I would like to say.
Okay, thank you very much, Hassan. So Hassan already said something about the speaker, and we thank you very much, Panos, for the availability to give this lecture. As already introduced by Hassan, Panos, Dr. Panagiotis Alevras, is an assistant professor in the School of Production Engineering and Management at Technical University of Crete. He graduated with a diploma in mechanical engineering from the National Technical University of Athens in 2011. And he received his PhD in mechanical engineering from the Heriot-Watt University in 2015. The topic was stochastic response determination of offshore renewable energy systems. Between early 2016 and September 2018, Dr. Alevras joined the Dynamics Research Group in Logbourg University, working on EPSRC projects related to the development of self-powered wireless sensor for automotive applications, and later on to novel vibration absorbers for automotive and powertrains. He joined the Department of Mechanical Engineering in the University of Birmingham in October 2018 as a lecturer, before moving to the Technical University of Crete. Okay, the topic that Dr. Panagiotis will address today is mitigation methods for vibration issues in wind turbine towers. I think this is a very relevant topic, and we are looking forward to Panos. I kindly ask you, the participants, to turn off the microphone because there are some noise in background. And of course, after the lecture, we can interact and reopen the microphones. Okay, Panos, the floor is yours, please.
Thank you very much, Enzo. Thank you, Hassan, for organizing this webinar series. It's indeed very interesting and very timely, I think, particularly for promoting the activities of the MODENERLANDS group and the cost action. Can I share my screen?
Yes, just give me a second now.
Good. Okay.
Oh, yes, you can now. Yeah.
So hopefully you can all see my screen now.
Yes.
Thank you very much for giving me this
Yes.
opportunity to talk about mitigation methods for wind turbine towers. My primary expertise is on nonlinear dynamics. So I worked since I graduated in 2011 on several different issues and aspects of vibrating systems, and particularly looking at the advantages, properties of introducing intentionally nonlinearities in the systems. So spanning from wave energy converters, other renewable systems, down to more everyday, more down-to-earth automotive systems. Today is a very cloudy and windy day in Crete, so I think it's a good mood to talk about wind energy. So I will kick off this presentation with an outline. So first, I want to give a very quick example of a very quick overview of why vibrations can be a bad thing for wind turbine structures. And I suppose that most of us here in this meeting would be able to appreciate this anyways. But just for the sake of the continuity in the presentation, I will start with some of the established and well-known aspects in dealing with vibrations in wind turbine structures. Next, I will give an overview of active and passive mitigation methods, more or less state-of-the-art in the technology, and what are the main problems and issues that we have currently in applying these in ultra-high wind turbine systems. And the central part of this presentation is a case study that we have. It's a bit of preliminary work at this point, but it's something that is ongoing and it seems very promising at this point. And it has to do particularly with the use of nonlinear energy sinks instead of the classical Thule mass dampers that we have in several civil structures. And hopefully at the end, we can have a lively discussion about what was presented or the extension of this presentation to other issues in wind turbine systems. So starting with why vibrations can be a problem, a serious problem in wind turbine towers. Typical wind turbine systems are exposed in a variety of loads. Onshore mainly have to deal with the weight of the own structure and the wind that acts upon the structure. But since we are moving offshore, and this move to offshore locations and offshore hotspots has been the primary motivation for building up this network, because once we go offshore, several things change in terms of what we could expect and how we design a structure. So as we go offshore, we probably, and particularly for the MODENERLANDS action and the energy islands, we are talking about floating systems. So in this case, apart from the wind, we definitely have currents that are applied on the submerged part of the wind turbine of the floating platform, and waves that also act, and they can be very, very important, very dangerous about the structural safety. Now, the general aim when it comes to vibrations is to keep them as low as possible, because on the one hand, we want to reduce the cycling loading that the structure experiences, and on the second hand, we want to mitigate excessive deformation. For example, some excessive deformations can lead, even though we have a very sturdy structure, can lead to the structure being outside the design criteria regarding buckling or other possible failure types. Now, the standard way, but basically what is currently being followed mostly in terms of the design of the structure, of the support structure of wind turbine, has to do with what you see in the figure in this slide. So let me get my pointer. It's basically the approach is to look at the frequencies at which we expect loading to occur, and this is mainly in the area of the 3P, which is the blade passing frequency. This is essentially caused by the thrust load that acts upon the nacelle of the wind turbine system through the blades and the aerodynamic loading. And we also need to worry about the 1P and the fore-aft frequency of the structure, the natural frequency of the structure. And typically we used to have in the early development of onshore, during the development of the onshore wind turbine systems, there were three main approaches: the soft, where you wanted your system, your support structure to be designed below the 1P, the stiff, which was above the 3P, and the soft stiff, which was in between. And the most common area is the soft stiff because it is a better trade-off when it comes to cost, where you have over here in the stiff case, so more material, more sturdy structures, and the soft, which on the one hand might be better for vibrations, but you might experience other issues, other failure types. So typically, wind turbines are designed in this area between the 1P and the 3P, and that's a very good approach in order to suppress, in order to avoid resonances that might occur in these areas. Now, two issues that occur when we go offshore and when we go to ultra-high systems is that it is very difficult to keep your natural frequency high enough. As the wind turbine becomes bigger and bigger, we have limitations on the diameter of the tower that we can build, and therefore it's the tendency of the natural frequency, the first frequency, let's say, the first modal frequency of the system, the tendency is to go down. Yeah, once it goes down, it might meet the 1P, or even worse, it might have some unlucky meeting with some of the wave frequencies. And waves can be very, very difficult to mitigate, particularly because they are randomly distributed. They follow probability density function that can cover even extreme cases. In the low probability case, can be catastrophic. And the second problem is exactly that we have to look at what is typically referred to as multi-hazard analysis in order to mitigate loads from different directions, from the wind, wave, or currents. Some example of failures. This is a wind turbine that had collapsed in Taiwan. This particular case was attributed to faulty bolts that weren't properly designed. Now, material fatigue, the authors had done in this particular paper had done an analysis for over 62 collapse cases, and material fatigue, purely material fatigue, was identified as only 7% of the failures. But it is very difficult to be able to understand how fatigue may affect cases like bolt failures or other systems failing to do their job. So fatigue is, which is directly related to vibrations of the structure. It's more deeply and more difficult to identify it as the root cause of a potential failure of a particular failure. So therefore, in the last few years, there has been a lot of research, particularly in the last decade, on designing systems that can control the vibrations of the structure, not only of the tower, but of the blades as well. But the blades are relatively easier to control with respect to the tower due to their size. So, for example, one of the most common methods that is being used to control the vibrations of blades is active control. Active control means that, for those who are not very familiar with control laws, has to do with the application of an actuator force according to a control policy in the feedback loop in order to counteract the external load that creates the deformations, the vibrations of the structure. For example, here, the authors have considered a tendon system which pulls, depending on the direction, within the desired direction that wants to be pulled in order to counteract the vibrations. This is more generally applicable on blades in terms of the active control because of the very difficult the difficulty that we have in order to apply it on the tower. It's a much more massive system. It's more difficult to apply the loads. It's not as economical as it would be for blades. There are cases where active control has also been applied for mitigating the vibrations of wind turbine systems, and at least in theory, they seem to be working quite well. So, for example, we see an application where in this graph you can see in blue the uncontrolled vibrations that a floating wind turbine is experiencing under the wind and the wave excitation. Two different control policies, the linear quadratic one and the decentralized one, were evaluated, and we can see that there is a very effective reduction of the vibrations of the nacelle, the displacement of the nacelle, which in turn can be interpreted as a much lower cycling of the stresses that are developed in the tower, which is essentially what we want in the end in order to ensure that at least we get a better life cycle for the structure. Now, the problem here, in theory, in models, is very effective, but in practice, it becomes quite difficult to be able to apply the control policy that we want to input in the twin mass damper, for example, in this case. And therefore, the majority of the work that has been done recently around the vibrations of wind turbine towers has to do with passive systems that do not require an external source of energy. They do not require an actuator. It's in their nature, in their design, to be able to control the vibrations of the primary system. And when we talk about passive control systems, we are mainly talking about what you might have heard as the twin mass dampers. So twin mass dampers are based on developments done in the 50s by Den Hartog. And the main idea is when you have an oscillator, is to attach a secondary oscillator of much smaller mass and tune the properties of the stiffness and the damping such that when the excitation comes along on the primary oscillator, most, or at least in theory all, but in practice, most of the vibration energy is transferred to the secondary structure, leaving the primary structure unaffected. So a sketch of how this could be realized in a wind turbine system, usually authors consider applying the twin mass damper in the nacelle and attaching the nacelle with a spring and the damper on the nacelle is expected to reduce the vibrations of the nacelle and therefore of the stresses that are developed on the tower, the bending stresses at least. The main idea in Den Hartog tuning is to match the frequency of the primary system and to properly tune the damping. Now, the problem with twin mass dampers is that although they are very effective in the tuning frequency, if you have an excitation that acts upon the natural frequency of the system, then the twin mass damper, you can feel very safe that the twin mass damper will do a very good job mitigating this vibration. The problem is that in many systems, particularly those that are interacting with environmental loads, you have multiple frequencies, and even as in the case of offshore wind turbine systems, multiple different loads acting on your system. And then the twin mass damper becomes an inefficient tool, at least for most of your loads. So it's definitely a no-fit-all solution. We cannot act upon the majority of the frequencies and the loads that are acting on the system. And this is a particular case where a twin mass damper was considered within the spar of a floating wind turbine, and the aim was to stabilize the spar using the TMD. And you can see that it was extremely ineffective in doing anything at all. And that is mostly because The loads that are tending to displace the spar, to rotate it, have a distributed spectral properties, which is something that the DMD cannot deal with. And therefore, generally, all the linear methods of trying to mitigate vibrations of host systems are extremely sensitive to the model properties of the system itself. So they can only, most of them, can only act against one particular modal frequency. And this is a problem when you have systems like wind turbines interacting with a variety of loads, and particularly stochastic loads, loads that are distributed, that have a spectral distribution across a considerable range of frequencies. There are some alternative methods, like the tuned liquid column damper, which is very well has been developed and designed to fit a variety of different platform designs. And we can see, for example, in this case, that in some simulations that the authors have performed, that we get the characteristic curve of a controlled, a linearly controlled system. So over here, I have drawn what you would expect without the tuned liquid column damper and what happens when you let it go. So the idea here is that you have two columns connected with a horizontal column that is filled with liquid. And as the system is vibrating, liquid is moved from one column to the other through an orifice that creates damping. And this introduces a frequency-tuned effect on reducing the vibrations of the system. The problem, though, and the reason why, although there has been some developments in using passive control systems, the problem is that it's not good value for money so far, exactly because the tuned mass dampers and the linear systems can act against one particular frequency, or at least in the very close region of this frequency. And therefore, the normal procedure is to tune them to the natural frequency of the structure. However, this doesn't mean that we can mitigate all or at least the majority of the dangerous vibrations that can occur in the structure. A good portion of them is indeed mitigated, but there's still a residue which can introduce significant fatigue damage and significant issues in the wind turbine systems. There have been a bit more advanced explorations and investigations. For example, apart from introducing a tuned mass damper in the spar, some authors have considered using pendulum dampers. And in fact, this concept of pendulum tuned mass damper has also been commercialized. There's a German company, ESM, I believe, who have commercialized pendulum tuned mass damper. It's still early in terms of the market acceptance, but there are signs that the market is accepting and is investigating such solutions. And this is also reflected on the fact that, for example, the OpenFast algorithm which is the main simulation tool that's being used for wind turbine systems, that was created by NRL, has included a specific subroutine for introducing tuned mass dampers in the response and the dynamics of the wind turbine towers. And therefore, it's expected that in the next few years, and as these structures become larger and more prone to vibrations, such systems, mostly passive, I think, although there is quite important work in active systems as well, this is going to be a more everyday solution for wind turbine systems. Now, the problem is also demonstrated in the results of the previous system. Even though there were two tuned mass dampers in the system, it was very difficult to be able to control both the fore, aft, and the side vibrations. So although when the pendulum was installed on the nacelle, as you can see in this figure over here, at the bottom left, the vibrations of the displacement of the nacelle was greatly reduced, but on the other hand, the side was not affected, it was almost unaffected at all. And this can be seen also in multi-load situations. So when the pendulum tumor damper is installed, we can see there is a massive reduction of the resonance of the structure, of the primary resonance of the structure. However, the response to waves remains unaffected. So the tumor damper cannot communicate with the energy that is input into the system from waves. And this is, and also turbulence, you can see at the bottom, at the left of this axis, because again, the tumor damper is a device that can be applied on one particular frequency, one particular mode of the structure, and it's very difficult to have tumor dampers to control different loads or different modes at the same time. And of course, there's also the directionality issue. So a key requirement in order to be able to have efficient mitigation of vibrations in wind turbine systems is to be able to have systems that are able to adjust to different loads, different properties in the excitation of the turbine, of the tower. So let me now move to a case study in which we considered a nonlinear energy sink versus a tuned system, a tuned mass damper. And let me start with what we used. We used the standard 5 megawatt NRL system, and that was it's something that most authors consider in order to have a baseline understanding of the analysis and the system they're proposing. So the standard 5 megawatt NRL wind turbine was considered. The analysis was performed initially on fast because it gave us the opportunity to have a more complete response determination, and including the mass damper as well. But what we did following, because generally fast is a bit more computationally ineffective in terms of the time that is required, we reduced the model and considered only the 4 aft. So using finite element analysis, one can simulate a wind turbine tower with a number of modes that is required. So in this case, we consider only the 4 aft vibration, so we can consider the tower as a simple cantilever with a tip mass. And what we are actually interested in is the displacement of the nacelle. So effectively, what we have in the analysis is a single degree of freedom system, which is equivalent. It's trying to simulate the response of the nacelle in the 4 aft direction, the first mode, the low frequency. Now, some background on the model that we have developed. We did the model reduction using the first mode. These were taken from NRL, the documentation of the 5 megawatt NRL, which gives you the mass distribution, the mass of the nacelle, and the structural properties. The first mode was also used from the NRL documentation, which you can see in the mathematical formula and in the graph below that. And using a model decomposition, we transformed the equations of the cantilever into a single degree of freedom system, basically describing the vibrations of the first 4 aft mode, and using this formula that we could have in order to compute the coefficients. Now, the first thing that we wanted to do is to have a sort of a validation of what we are doing here, because we didn't want to model something that was completely irrelevant. The 4 aft frequency in the model that we had was 0.33 hertz, whereas NRL gives it at 0.324, which is very, very close to what we wanted. This is basically something that we expected, but that's something that a first indication that we are on the right track of having a very simple reduced model for the vibrations of the system. Now, later we used a Kalman turbulence model for a moderate wind at 16 meters per second mean wind speed. we calculated this with version 8 of FAST, and this was used in order to excite the vibrations of the of the wind turbine structure. Now, the thrust load, we performed an FFT analysis in order to identify the frequencies. We were expecting the 3P to be very important, and we also expected to see the turbulence in the lower end of the frequency axis. And also we have some contribution from the free response, the fore-aft frequency of the wind turbine itself. So basically, we can do an analysis. First of all, validating the SDOF model, the single degree of freedom model that we developed, against the results from FAST, which is a much more complete set of calculations. So the tip deflection had a very good agreement. The nacelle deflection had a very good agreement with the data given by FAST, both in the time domain and in the frequency domain. And therefore, we concluded that the SDOF model that we had was reasonably good in order to be able to proceed to the evaluation of the vibration control methods. So, doing a wavelet analysis in the time history of the response, we're looking at how the vibration energy is distributed across different frequencies at the different time instances of the response, and we notice three major distinct characteristics. And this is the free response, the fore-aft frequency of the system, the 3P, the forced, the harmonic component coming from the thrust load, and the rotation, the variability, the deterministic variability of the aerodynamic load, and last, the turbulence, which is completely, which is the random part of the wind load. And the first thing we did is to have a baseline analysis for the Q mass damper. In order to introduce a Q mass damper into our system, we included the second degree of freedom containing the parameters of the Q mass damper. So basically, we're modeling the introduction of an additional mass on the primary oscillator, and we tuned it based on the Hartog tuning. So we chose a 5% mass ratio and calculated the necessary natural frequency damping ratio in order to have the optimum performance. And we can see that in the free response that the Q mass damper was actually tuned to. We have a very good mitigation of the tendency of the structure to vibrate. Of course, this is something that you don't expect to have in the normal operation of the wind turbine, but it's very indicative of whether an absorber control method that you're developing is capable of having good performance in mitigating the vibrations at the particular frequency that is tuned to. However, as we have seen in the wavelet analysis and the FFT of the thrust load, what we are mostly interested in is the 3P, the aerodynamic load. And when the Q mass damper is tuned to the natural frequency, you can see in the graph comparing the response with and without the Q mass damper that it is completely ineffective. It doesn't affect at all the response at this particular frequency. So you can see in the zooming, there's a very, very tiny difference, which practically tells us that you can either suppress the 3P or the natural frequency of the structure. And there you have a constraint that cannot be resolved with a standard Q mass dampers. And of course, turbulence, it's very far off the field of application of a Q mass damper. It's something that TMD, it's very difficult. Although there have been some control, some design approaches, the H infinity, but in that case, you wouldn't be able to control effectively the frequencies in which you have the major the 3P and the 4R. Now, having this data in mind, we started with a very crude evaluation of a nonlinear energy sink. Now, before moving to the results, let me briefly describe what a nonlinear energy sink is. So the main characteristic of a twin mass damper is that it has a spring with a constant, with a linear twin mass damper has a constant spring constant. That's why we call it a spring constant. So the force, the restoring force of the twin mass damper is K times X. So it's the stiffness of the spring times the displacement. The main characteristic of a twin mass of a nonlinear energy sink is that we break this linearity constraint and we are introducing intentionally nonlinearities in the restoring force of the absorber. So instead of having this linear curve, we are using a polynomial curve. Usually, at the first stage of implementation, a purely cubic restoring force is considered. And the main advantage here is that the nonlinear energy sink does not have a preferential frequency. It doesn't have essentially a natural frequency. You may define some instantaneous natural frequencies depending on the deflection, depending on the amount of energy that the nonlinear energy sink has. So effectively, the nonlinear energy sink is a vibration control method that is completely decoupled from the frequency of your excitation, but at the same time can work differently for different frequencies at different energy levels. So if you're vibrating at high amplitudes, you can act upon higher frequencies. If you act at lower deflections, the frequency becomes lower to the limit that becomes zero, at least in the theoretical models. This has found several applications, even in large structural systems. So you see here an application in a 6-story building where an NES was installed with elastomers acting as the nonlinear springs, pyramid elastomers acting as the nonlinear springs. It was installed at the top floor, and you can see there was a very good mitigation of a relatively transient multi-frequency load. So you can compare the top, which was without the NES, or with the NES not moving, locked, and with the active NES, where this was allowed to absorb energy from the system. And there is a very big framework developed by Professor Vakakis in the University of Illinois and many other authors to the development of this NES system. We have found many applications from structural and mechanical systems. And in this case study, we consider applying this to wind turbine systems and exploring potential benefits for the mitigation of the environmental loads. So in order to do this, we need to change the restoring force in the initial twin mass damper model. So by adding a cube in the restoring force, we start modeling a system with an absorber that doesn't have a preferential frequency. And the first step is to see what happens at the preferential ground for the TMD. The TMD is effective, mostly effective at the tuning frequency. And the first step is to evaluate whether the NES is equally effective at this tuning frequency without essentially having a preferential frequency. And this can be done by looking at the free response of the host primary system and comparing it with its response and the performance of the twin mass damper and the NES. And you can see that although the TMD is slightly better at the free response, the NES is almost equivalently efficient in mitigating the initial vibrations, the free response of the wind turbine system, the structure. And therefore, that's a first tick for the NES because it has essentially cancelled the advantage of the twin mass damper. Now, the second step is to see what happens at the alternative response regimes. And in this slide, we are applying a harmonic load at 3P. And we notice that when the TMD was completely incapable of reducing the vibrations of the primary system, the NES can lead to up to nearly 50% reduction in the amplitude of the vibrations. And therefore, the first thing that we can establish from this result is that we can have a vibration, a passive system that doesn't require an external amount of energy, external input of energy, that can act at different frequencies, at loads that act on different frequencies. And this is a very important result, which is encouraging us to continue with the analysis further on. Now, we have also looked at how the NES can interact with turbulent energy that comes from vibration, energy that comes from turbulence. There is a marginal improvement, although it's not what it could have been because of the limitations that we had in this study in terms of tuning the NES to work in with turbulent loads. We are very optimistic that this development has a we can expect that it will have a very good performance for turbulence as well, because the NES has been also tested for blast explosions or blast loads from explosions and other things that are very broadband. And therefore, we can expect that the proper tuning of the NES can also be able to act against completely random events. So, just a slide to recap some of the things that we have seen, particularly for this case study. We've seen that the NES was able to act against multiple frequencies, something that a tuneless damper passive system will not be able to have done. There was a definite conclusion from the data that the NES can outperform the TMB when it comes to different frequencies. And what we have identified as the next step for investigation is to tune the NES to act against turbulence and extreme transient events. Thank you very much. I hope it has not taken longer than you were expecting, and I'm happy to answer any of your questions.
Thank you very much, Panos, for your very interesting and clear presentations. So I think now it's time to open the discussion with the participants. And first of all, I would like to ask if anyone has comments or questions to Professor Dr. Panagiotis.
I can kick off if no one wants to.
Please, Hassan.
Right, Panos, thank you very much for this very interesting, nice presentation. I understand that damper and spring, they are mass spring damper, they work in a range of frequencies, but not all the frequencies. And you have here different frequencies from small to high frequency. Would it make sense to have an active damper and active spring in this case? Then they can adapt the coefficient for the spring and the damper to work with different frequencies instead of only a range of frequencies.
Yes, indeed, and there has been what you're referring to is the semi-active control methods, where instead of actively controlling the energy in the structure, you are controlling the properties of your absorber. The issue with that is that you don't know when a massive wave will come. You can't expect when a wind gust will come through that will introduce other frequencies in your system. So that would have a good applicability if you had controlled conditions in your excitation. It could possibly be more efficient if you had some statistical analysis about the average frequencies according to a seasonal variability. But then again, you need to think about the cost. And the cost of such a system I'm not sure if it would be enough to justify the performance. So usually when an active system or a semi-active system is introduced, the cost becomes a primary issue. And also we are talking about more advanced electronic control policies that are not is a key issue in active control is stability of your controller. I'm not a control guy, but control, the controller is stable only at the scenarios that you have been able to model. So it becomes a bit more difficult to ensure the proper operation of the control system.
Thank you, Panos.
Thank you. Other comments, questions?
Well, a question from Paul in the chat.
Yeah, see, yes, sure. Which FEM was used?
We didn't use FEM, we used FAST. FAST is not
Okay.
using FEM.
Any other comments? I have some, but I would like to wait at the end. Anybody else wants to comment or has some curiosity?
Yeah, thanks. Thanks, doctor. So my name is Amya. So I'm working something related to using the tune mass damper for controlling the tower vibration. So recently I have been working to optimize the parameters for the tune mass damper. So let's say I want to tune the frequency ratio or mass ratio. So like for your case in the nonlinear energy thing, is it possible to optimize the parameter to get more better results in case of like turbulence?
Yeah, not only it's possible, but it's necessary because the tuning of an NES it can be a much more cumbersome task because you have to involve nonlinear invariant manifolds. It's not the standard way of looking at the frequency response. We don't have an analytical solution as you have with the tune mass damper, so it's not a simple task of setting this equal to 0, the frequency response, or minimizing it. It's absolutely necessary to have a tuning framework, but the key issue is that you're not tuning your NES to a certain frequency. You're tuning your NES to a range of operation, and particularly a range of energy operation. So, for example, you can tune it to high energies, meaning that you are suppressing vibrations that come with high energy, and you are leaving the low energy vibrations to pass through, which is something that would be very beneficial for your structure. And the good thing is that you can take a random load, you can take a broadband impact load, and have a very good separation ratio. The magnification factor becomes, or the reduction factor becomes, can become very efficient. But yeah, necessarily you would need to go through an analysis of your response. There are different graphical methods, wavelet analysis, or even semi-analytical, quasi-analytical ways in order to go through that. And that's basically one of the issues in the development of NES systems, because they have a relatively complicated design procedure.
Yeah, thank you so much. Why? Because like few days back when I was trying to simulate the tune mass damper with a damaged like a damaged parboy, so I was not able to like reduce the pitch motion. However, it is like reducing the surge motion. So maybe like the NES is going to do a better performance for that, and I would like to thank you again for this beautiful presentation.
Yeah, thank you too.
Yeah.
Right, so before Enzo, can we take
Yeah.
a photo, please? So if you, Panos, can stop sharing the screen and
Yeah.
so if you can open your camera, that would be great, please. Any more to open the camera? Right.
Done?
Yes, so people are still joining. Yeah, it's done. Thank you.
Okay, thank you, Hassan. So I have another comment regarding the presentation. A very general one is about the very first picture that you showed us regarding the spectra of the exciting loads, wind and waves, and the typical design frequencies range where you normally try to locate your design. In that gap, in that range where normally wind turbines are designed, yeah, exactly that one, there should be considered something that most of the cases not accounted for, is that the nonlinear wave forcing, because the excitation of the waves is mainly concentrated where you see the peak, which is the main frequency of the sea. But if you model nonlinear waves, you will see some small peaks around 3 times that main frequency that you see there. So if you see that main frequency at 0.1, if you consider fully nonlinear waves, some small peaks will appear around 0.3, 0.35. These contributions are the higher order harmonics, which are generated or are contained in the realistic sea states, especially, of course, severe sea states. And these severe sea states normally are associated with wind speed above the cutout velocity. So normally the wind turbine at that velocity is turned off. And when it is turned off, it has a dramatically low overall damping capabilities. So it happens that these nonlinear wave contributions perfectly meets the first natural frequency of the turbine that, as you said, is around 0.32 hertz. In that case, I assume it was on a fixed bottom. But in offshore, for offshore, I mean, 0.32 was, I guess, for onshore. If you have, if you have fixed bottom offshore on 20 meters water depth, the same 5 megawatt wind turbine, then first natural frequency is slightly reduced to 0.28 hertz. And this 0.20 hertz is very much in line with this third order contributes from the waves. And what we saw in some numerical simulations is that when the turbine is parked, so with this very low damping capabilities, it gets this excitation, which is very dangerous because some ringing-like oscillations are triggered by this nonlinear wave contribution. So the comment was that in designing the devices to damp out some oscillations, it would be interesting also to consider these effects that can occur in these situations of sea states. I don't know if you have ever considered that, or if you know if normally this contribution can be accounted in setting the parameters of either tune and mass damping or the energy sink. Probably energy sink is easier.
Yeah, no, we definitely didn't consider that, and to be honest, it's largely ignored, the scenario that you just described, and it can be very dangerous indeed, because if you have a peak in the spectrum over there, somewhere about a natural frequency of your system, that can be very dangerous. Yeah, that would be because typically waves are modeled with a Pearson-Moskowitz spectrum. They're not considering these peaks.
They are the main one.
Yeah. Yeah, that would be, and I think the NES would be able to account for multiple harmonics, because we have seen in a completely different setting in automotive applications that we have applied NES in the past with colleagues in Loughborough University. We have seen that because over there in the automotive powertrain, you have gears messing, you have multiple harmonics. We have seen that an NES can be effective to counteract against multiple frequencies and harmonics of a certain load at the same time. And this can be an interesting application for an NES to act against the main wave peak and its nonlinear interaction harmonics.
Yeah, and I have also another comment. I think it's somehow related to what Hassan said earlier. When you design your energy sink or even the tuned mass damper, you make an assumption on the let's say spring and the damping properties of the main oscillator, right? And then you tune the parameters of the secondary oscillator. But since the wind turbine has the damping and maybe the spring not, the stiffness not, but mainly the damping, much related to the status of the turbine, the state of the turbine. If the turbine is parked, it has a very, very low damping capabilities. If the turbine is in power production, the equivalent single degree of freedom model will have 10 times larger. And moreover, there is also variability of this damping, equivalent damping, considering the different rotation speed of the rotor, which are associated with different wind speed. So my question is there the possibility? So you cannot have a unique main oscillator on which you tune the damping, the damper. So how it is possible at least to subdivide in some different typologies of behavior, because during the power production you can have different pitch control of the blades, yaw control, and so on. So you cannot have only one single model on which you tune your system.
Yeah, definitely. What Hassan said is possible. You can retune there are systems that are able to retune. For example, particularly when it comes to damping, they have been using magnetoidological dampers that tune their own damping based on the external electrical stimuli, and they're very energy efficient. And but the thing is, with what you described is very important for tuned mass dampers, because in order to design a tuned mass damper, you need to have a preferential frequency to which you are going to tune it. For an NES, the situation is different. Again, when you do a model, when you do a simulation, you need to assume something for the system, the structural system parameters, but it's much less sensitive to variations of the natural frequency of the primary system and its damping. So typically, when you are designing an NES, you are conducting a parametric analysis against different damping ratios and stiffness values, and you are looking at maps, regions of effective performance. You're not looking at single point performance. So there is room for variability in these parameters.
I see. So you potentially could include several states of the main system, like power production, different rotational speed, and so on, and try to have a design which optimize the tuning considering this envelope of
course, there's always an upper limit of how you can manage this, but the key thing is that a nonlinear energy sink is tuned to the input energy, not to the natural frequency. So if your energy is high, you're efficient. If it's low, you may not be efficient, but you don't care if the energy is low or not.
I think we are 5 minutes after the time now, so so we can continue the discussion, but I think it's for the benefit of everyone. I think it's better to stop it now. Stop it here, and we thank Panos also.
Yes, thank you very much, Panos, and all the participants.
And thank you very much. So the next seminar will be hopefully next month in March with working group 3. So we'll contact Robin. So I don't know who will be the presenter. So Robin will advise everyone. Thank you very much, and we'll see you next month.
Thank you very much. Bye bye, everyone. Thank you, Panos.
Thank you. Bye bye.